multiple linear regression. In a way, it's just like we did last week, but now there's more than one x. Apart from that, everything is the same. The function is the same. The way we interpret almost is the same. But let's spend a little time anyway. Here is the model, which is the generalization of what we did last week. Now I need a bit of more notation because I don't only have one x, I may have up to p x's. In our case, we have 3 x's in play for this particular. The p could actually be really large. And in machine learning, it could be thousands, hundreds of thousands, millions, actually, sometimes. But today it's only 3. But it's a big step to go from 1 to 2 and 3, actually. There are some things to think about when we do that. When we've done that, we can move on from there more easily. So that's the statistical model. We still have the same assumptions about the residuals. How would we estimate such a model? That would be the first thing. How should we fit the model? How should we compute the coefficients of the model? Yeah, I'm going to look at the picture and then I'll go back to the slide. Well, it's just still a linear model, but now in more than one dimension. Here is shown one with 2 x's, and then of course to visualize it we need a 3D plot because there is also a y, but it's a 2-dimensional. This is x1 here and we have x2 here, right? And then we have the y as the third axis, x1, x2 and the y. So we fit the plane, we find the plane such that the residuals, that is the y vertical distances to the plane, becomes as small as possible. The plane is as close as possible to the data points. The same idea as last week, but now in higher dimensions. And mathematically, this is expressed like this. Here is the criterion, the squared y differences. So it's y differences, vertical y differences that we minimize. And now last week we only had the beta 0 and the beta 1. Now we could have a plane of arbitrary dimensions. P needs to be smaller than n for this to be even mathematically possible to solve. And we are not gonna do it with you. I mean, this is P plus 1-dimensional optimization. Well, for a mathematician, that's pretty straightforward. We could just take the derivatives of all of them and equal to 0 and solve the system. It's going to be a linear system, but this is not part of this course. We'll just have to understand that that's what the function is doing for us. And actually today we'll not even write out the solution formulas. Last week we wrote explicitly what the solutions of beta 0 and beta 1 were. Explicit and very simple formulas. Now they are not as simple today, generally speaking. So we don't even write them out. So what we do is to let the computer find the beta coefficients for us. Then we can also easily extract, and the computer can do it easily for us, what could be the actual plane values, the predicted or the fitted values. And then we could also look at the residuals, that is the deviations from the plane, which are depicted here, right? We could find the plane is given by beta 1 and beta 2, where it sort of hits the y-axis is given by beta 0, the intercept, and then we can summarize how far away from the plane each point is, and we call that sigma squared, the residual standard deviation or variance. So that's what we do. And here is a very information-heavy slide put into a few points. I don't show all the method boxes and theorems now. I'm just mentioning them on a single slide. First of all, I repeat what I said. I'm not giving you in this course a formula that you need to be able to use explicitly to be able to compute the betas of an MLR. Instead, I'm telling you in a remark that what you should be able to do is to extract those coefficients and their standard errors, their uncertainties from the R output, from the summary. We'll get back to the, you can already do that because I taught you for 1x last time, and it's the same story today. Then we have a theorem that is a copy of a theorem from last week telling us that we can do statistical analysis called statistical inference about those parameters in the same way as we did last week based on t-distributions. There is a theorem saying that. Then there is the methods that tells us how to do hypothesis testing and confidence intervals for the coefficients. Again, these are not given by very explicit formulas, or they are given by explicit formulas, but they are based on that we can extract these values from the R output. So it's a kind of meta method box in a way, right? Where we don't know the very detail of it, but we know how to look at the output. And as I've said a couple of times, this is just doing what I taught you last time, but for all the x's in the output. So in a way this shouldn't, that's why I do it like this very rapidly, because I hope it shouldn't impose the big challenge here actually, although we don't know all the details. And then again, but it's not part of syllabus, you could find, we include that in the 3 weeks course where we do a slightly more technical version of some of the stuff for the Math Tech students and others that are so lucky to be in the 3 weeks version of our course, which is called 2403. So that's why we everywhere, a few places have a bit more math detail that I'm expecting you to go into, because we have another version of the course where we add this little extra in the course. We do show you, so if you're interested, it's not rocket science, it's a little bit of algebra, linear algebra. Then you can in fact express everything explicitly quite easily. It's not something I expect of you in the course, but it's just to tell you, of course, it's not too difficult to actually do it. Very important, and maybe the thing where there is a difference, where we need to think extra compared to last week. That is how to interpret these coefficients. Well, the first here is actually just a copy of last week. Generally, coefficients is a bit like, I mean, as you were taught in elementary school, they are slopes in a line, at least last week, right? It's slopes in a line. We all know the line. We know what the slope of a line expresses. It expresses the change of y with a change of 1 unit of x, right? That's the slope of a line. That's what it expresses. And so also in a multiple linear regression, but with a bit of extra. And here comes 4 sentences that are thought to express the same thing. That's why they came together. And pick the one you like better. And that's fine. The new thing is that the betas in an MLR is actually sort of conditional on the value of the other x's. So when I'm talking about the beta in a 3 multiple linear regression using both wind temperature and radiation, the wind beta is expressing the expected change with 1 unit of wind, but given that I assume that radiation and temperature are kept at the same values, right? So it's for kept given values. It's like we correct for the other values. It's all other variables being equal. It's the unique effect of xi. We have cleaned out the effect of the others. There are many words of the same that you'll hear researchers use when they correct for demographic background, when they do certain conclusions. It means that likely there is a linear regression effect of such a thing, because then the other effect, that is really the interesting part, has been corrected for the other one. So it's not an artificial effect due to some of the other things. It's a clean, it's a pure effect, at least as pure as possible, in the sense that we have corrected for what we included in the model, and we have ignored what has not been included in the model. And that takes us to one final warning. that there is a very big step between using regression and multiple linear regression in a kind of association kind of way, where we just observe that it appears that higher ozone values comes with higher wind or lower wind or whatever, and then to actually make causal, or if you're into epidemiology, intervention effect conclusions. Maybe when we actually change the system, what if we change the climate in the US with a few degrees down? Would we then be sure that the ozone would also correspondingly follow, like this model would tell us? No, we couldn't be sure actually, because even though we intervened with the climate of the world, maybe there are some other effects going on that we are not on top of in this modeling. And it requires a hell of a lot extra to start to really do causal conclusions. And that is something that, I mean, you can take whole classes of learning about how to really try to do causal conclusions based on observational data. Causal conclusions on experimental data can make quite good sense often, but causal conclusions on observational data like this is highly, highly risky business, and as a general rule, you couldn't do it. That's why it took so many years to actually prove to the tobacco industry that smoking actually was causing cancer. Apart from the obvious thoughts of relations, there were statisticians around, and I assure you the tobacco industry, they funded and financed and found anyone who would have that point of view, and there were a few, that you could never prove something causally related by observational studies. And when would you want to do the big clinical study where you force 1,000 people to be exposed to a high degree of smoke and then see how many of them died within or developed lung cancer? There are certain experiments that you don't do. You do them on rats, you do them on dogs, you do them on monkeys, I'm sorry, you do them on pigs. I'm also sorry, but people do. But then you can always argue, well, so pigs get lung cancer from smoke, but pigs are not humans. That's true. Monkeys? No, monkeys are not humans. I don't believe it. It's observational. So it took a long time until finally they got caught up by common sense. But nevertheless, it can also be highly risky to make causal conclusions based on odd relations we see. It's the storches who bring in the babies in Denmark, for instance. Of course, we know if you look at the number of storches and the number of babies, it's pretty clear that's what happens. So, let's... true statement again. Temperature has a small p-value. We even get a help with the double star here. And it's a positive relation, right? So that's why both the red and the green are correct statements here. And the other one was not significant radiation. And the intercept, yeah, not significant, and that's not really interesting either. So, good. Who was up? Well, good job.